release of a toxic compound, you know how to handle, how do we estimate, are they overexposed? And as we had talked about, if there is a release, if you have some kind of incident where you have release of a toxic material, your workers are most definitely going to be overexposed, right? Because what we're looking at are now not ppm levels of compounds, right? It's much more than that, and it depends, right? If you have a liquid and you have an evaporation rate, you can still be in the 1,000, 40, 50, 100,000 ppm, right? If you have gases, you're probably looking at concentrations. So bottom line, the time-weighted average values that we worked on in chapter 3, right? Those are the levels that you can be exposed to for 50 working years, okay? If you have a release, if you have an accidental release of a material, right, those values are very small. So what we really need to look at now are emergency exposures, right? If you have how can we keep them safe and not kill them if there is an accidental release? So really all the source models that we have looked at in chapter 4, whether it's liquid or a gas, right, they're going to give us very high concentration. And in a lot of cases, not only are the workers at danger, the community at large can be at danger too. So we're going to talk today about what do we have, right? What information do we have at hand to guide us in when do we need to evacuate, right, the whole city? Because that is not something, right, that's a very costly effort to evacuate a whole city. But you might have to, right? Okay, so we started talking about, and basically we skipped a whole case 1 through 10. We're not going to worry about those. We're going to handle 11, 12, 13, and 14. And basically that we're going to use the Pascal Gifford dispersion models. That's what those cases are. And we're going to differentiate between if we have a plume, that's a continuous release of a component. That could be a gas tank leaking, there's a hole, somehow a hole open up in a gas tank, for example, or a pool of liquid is evaporating and no one is noticing it. After a while, you're going to form a plume that will travel downwind, of course. The other case is when you have a puff. So that usually comes from an explosion that releases material, right? All at once, and you're going to have a huge vapor cloud that's going to travel, again, downwind. But we have to look at those separately. So what we've talked about is what is affecting the concentration, because that's what we are concerned with, right? You don't want any lethal concentrations of materials such as what happened in Bhopal to reach the community, right? And of course it depends on the wind speed. Now the wind sometimes helps us, and sometimes it's worse. It makes it worse because obviously it also makes it travel faster. So sometimes when that happens, if it travels too fast, there's not enough time to dilute the gas. We talked about atmospheric stability, how that comes into play. So your release is going to be different, or the concentration is going to be different if it happens during the day or at night, if it's sunny or cloudy. So the worst case scenario that you can have is a release at night, right, where there's a lot of clouds. There is not a lot of vertical mixing then, and basically you have a lid on your release that's going to keep the concentration high at ground level. And then ground conditions also comes into play, and that is a lot of high rises, for example, disturbs the wind, so you get a lot more turbulence. And what we want is vertical mixing, because that will decrease the concentration faster and make sure that, right, the toxic component actually goes up and not just is sprayed throughout the community. Height of the release. So there's a reason why incinerators, for example, have chimneys that are very tall, because if they're very tall, it takes time for it to actually come down, right, to ground level where we can smell it, for example. But it usually has time to dilute enough so that it's not highly toxic at that point.
In last class, you said that I think in one of the problems was like, it was 100 meters tall.
Yes.
Is that like standard? Because that seems like super tall.
That is super tall. You know, I don't know what standard chimneys are actually, but a lot of them are very tall, so 100 meter probably isn't unreasonable. Right? But that was effective height, so that could also mean that you're having momentum coming out. So if you have a high pressure, for example, and gas is shooting out of your chimney, that's going to increase the height. If your factory is located on a hill and the community is at the bottom, that is also going to increase your effective height, right? So there's a lot of things coming into that. 100 meter, that does seem tall. Probably at least 30 though would be my guess, right? I've never tried to measure one. But that's why they're tall, and that's why, right, we want it up there, have time to mix before it actually comes down. Because they're eventually going to, right, come down and spread. The other thing, which we are going to assume that we have neutrally buoyant conditions. But of course, the difference in density between the gas and ambient air, right, is going to determine whether or not your initial gas is going up or slumping to the ground. But eventually, after a certain distance, you're going to reach something that can be assumed neutrally buoyant, so that you don't have that density difference. Okay, so the Pascal-Gifford dispersion models, we talked about 4 cases. Case 11, so forget about case 1 through 10. You don't have to worry about those. Is Puff at ground level, then we had Plume at ground level, and these are the equations, right? We talked about what we need. So instead of using any eddy diffusivities or anything and having to worry about, differential equations, we're going to use dispersion coefficients and determine those from tables. We have some equations for them, and all you need to do is know how to pick the right one for the conditions. Okay, so we have those 2 cases, and then we have Plume and Puff with release at a height. So those are the 4 cases that we're going to cover. Okay, so we have continuous release or an instantaneous one, release at ground level or at the height. So we started, let me see, and again, the dispersion coefficients are dependent on the atmospheric stability, and here is where we take into consider the wind speed and what is daytime or nighttime. And the worst case here is case F, where the release is at nighttime when there's very little wind speed. Yes?
Can you come back a slide just for a second?
Did I misprint a,
I just don't see the person that says function XYZ.
so X, the X comes into the dispersion coefficients. The dispersion coefficients are functions of X. Okay, so that's where your X comes in. Good observation. And that's the only place, right, where X is. Except where you have, wait a minute, where's the Puff? Ooh. Wait a minute. Okay, I need to look at if case 14 is the right equation, actually. Because notice the difference here, the Puff, you have X minus UT here. Okay, so it depends on what coordinate system you have chosen. But what we're interested in, of course, is the center of the cloud where the concentration is gonna be the highest. And the concentration, the X, right, the maximum concentration is always going to be where your X is equal to UT, right? That's the wind speed times the time. That's where your cloud is at any time, right? And so don't quote me on this one. I need to double check the case 14 is right because there's not any X minus UT on this one. So let me check on that. Okay, so we need the dispersion coefficients, these sigma y, sigma x, and sigma z. And we need the atmospheric stability for that. And what I was gonna say here, if you notice, nighttime with low wind speed is actually, it's the worst case scenario because that will give you the highest concentration. At night, increase in wind is actually helping you because it's right, that at that point you have a lid on it, you have very little vertical mixing, so the only mixing you will get will be the horizontal one, so the wind will help you. During the day, case A is the best case scenario, which is extremely unstable atmosphere. You have a lot of vertical mixing. In that case, more wind is actually hurting you. Okay, and the reason is you're moving things faster, right, than it can dissipate. So that's the reason. So once we have determined what atmospheric conditions we have for whatever problem we're looking at, we go in. There are graphs that we looked at last time, but I really prefer if you use the equations. It just, otherwise you're reading log graphs, and you know the error in that is usually higher than if you plug in x in an equation. Okay. So you can see there are complex equations of x in some cases, but you pick for plume, you have to decide whether or not you're looking at rural conditions or urban. Okay, so the worst case here would be rural because we don't have a lot of buildings. Buildings increase the vertical mixing, so if you're looking at for worst case scenario, that's what you would pick. Worst case scenario would be rural conditions in F. Right? But that may be defined in the problem that we're looking at. So, but you have two tables, one for plumes and one for puff. Okay, so you just need to see which one you need to use. And for puff, it turns out that we're not differentiating between whether or not it's an urban or rural release. So that makes it a little easier, and you know, it's easier to solve for x if you're trying to solve for distance x, right? If you have a puff release versus a plume, and we'll see that. So of course this was perhaps a lot of information to take in. Before you actually start working on it, it's hard to see how it works. So we started with 5.4 last time. So in this case, we have a trash incinerator with an effective stack height of 100 meters. Okay, it's an incinerator that will most definitely be a plume. It was a sunny day with 2 meters per second. That gave us that we have atmospheric stability A. And we were told that the concentration of sulfur dioxide was measured 200 meters directly downwind. So, and we would have to assume that that's on the ground. It wasn't said, it didn't say it was at a height. Most likely, we want to know the ground level concentration because that's where most people are, right? And it was measured to be basically 0.5 milligram per cubic meters, microgram. Cubic meters. Okay, so that's fairly low. That means that in this equation, right, what we have is C 200, 0, 0. Okay, X, if you look at this, X is 200, Y is 0, Z is 0. So what we measured was this, which simplifies this equation to this and that concentration. And we were asked to solve for QM. What release would give this concentration? So we did that, and it's about 12 grams per second. Okay, now what we didn't do, because I didn't have the numbers, is we didn't look at, what is the maximum concentration from this release, and where is it located? So you don't have to, obviously, you could take the derivative of the equation for C, right, and set it to 0 to get the maximum concentration. They have done that for us, so you just need to pick the equation 552 and 553 in the book. So to calculate the maximum concentration though, right, we have the height of the release itself, but then we need sigma z and sigma y. And those are dependent on x, right? So we also need to know the location of that maximum, so we have to calculate that first. That equation for the maximum is actually pretty simple. It's sigma z is equal to HR over the square root of 2.
So when it says 70 in this case, is it like, you don't really know the specific location, but it's like
So
70 meters away from it?
So that's the dispersion coefficient of 70.71 meters, right? It's hard to put that in really what right, what that really means. Because, right, dispersion, I mean, there's standard deviations, right, in distance basically is what they are. They actually do have meter as the unit. But to actually get that is not the distance we're looking at. But we know the equation for sigma c, so we can calculate what x is for these conditions. I'm gonna leave the numbers up there. And let's see if we can get some numbers on this particular case. Yeah. 5.4, we have sigma c at the maximum, HR square root of 2, 7.71, because our HR is equal to 100, and we had last time, when we pulled out the equation for it's equal to 0.20x. That's what we had from the table. If we go back, we can confirm that. We had so let's go back to here, just in case you weren't here last time. We had 2 meters per second, sunny day. That means our atmospheric stability is A. Okay, it's definitely a plume. And what did we choose? We chose rural conditions. It wasn't mentioned. We chose that because that would give us worst case scenario. Okay, so that 0.2x is from here, right? This value here. That's our sigma g. And then of course we're gonna need sigma y too, because that comes into the equation. So that comes from there, 0.22x. And there's only one thing you might want to make a note of, that this is to the power minus 1/2 on all of them, but not in this column. There's actually a plus in here. Okay, and from looking at the actual graphs, it doesn't look like that's a misprint. The curve is shaped up instead of down, or sloped differently. So I don't think it's a misprint. Okay, so this gives us that our x is equal to 353.55 meters. Okay, let's call that 350 meters downwind. Okay, so that was the one answer. That's the location of the maximum. Okay, and then what we needed to calculate Cmax